Good afternoon, everyone. I am Mr. Ish. We're looking here at sectors, the determination and the derivation of the area of a sector formula and the arc length of a sector formula. One of the great versatilities or benefits of integral calculus is that integration or integral calculus techniques is a study of the limit of sums. So when are we talking about areas or even volumes, the derivation of those relevant formula or formulae become available to us via integral calculus. I've already presented a video on the derivation of the circle area and the circle circumference formulae. Based on what has been presented over there, it's very easy to convert that derivation into that of a sector. And the reason why that is based on the difference between a circle and a sector. And when I'm using the word difference, I don't mean that in a mathematical way, I mean that in a literal way. The difference between a circle and a sector is this. If you have a complete circle, you know that represents in terms of angle a 2 pi. Especially when you look at it in terms of a unit circle, 2 pi. If you were to take a fractional proportion or a fraction of this circle, and that's what I'm talking about, the difference. The difference between a circle and a sector is that a sector is a fraction of this. And we were to bring this fraction out. What is a fraction which represents a circle or which differentiates a sector from a circle? It is this. The sector represents a fraction of that whole. The whole is 2 pi. And you know this right here, a circle is represented by 2 pi in terms of the angle. A full revolution, a sector represents only a fraction of that whole, the 2 pi. So that right there provides the means by which we can do the derivation of a sector's area and the arc length. You know what we're talking about area in terms of a sector. We're talking about the cumulative limit of sums of all of this part in between. But what are we talking about arc length? We're talking about the circumference of a sector, but we're not talking about the circumference of the internal aspect. We're only talking about something from right here to here, which you know is symbolized in math as S. Because S is equal to R theta is a formula for the arc length of a sector. And in terms of the area of a sector, we can just write that S is equal to half R squared theta. If supposedly you know how to derive using integral calculus the circumference and the area formula for a circle, all you have to do, assuming you've done the derivation, you do pi r squared representing the area of a circle, you multiply it by this factor. This is the great factor which makes the difference between a circle and a sector, and you multiply it. Here's my dot for multiplying by this factor theta over 2 pi, and you simplify it. Here the pi cancels out, here this pi cancels out. What do you get left with? The over 2 comes out as a 1 over 2, and you have r squared theta on the top, which very well mimics this formula right here. And then when you're looking at the circumference of a circle, 2 pi r, you again multiplied by this factor, this fractional factor that I'm talking about, which differentiates a circle and a sector. You multiply by this theta over 2 pi. In this instance, this 2 pi cancels out with this 2 pi, and you're left with just r theta. And this represents not a C, literally not a C, but it represents an S. So right over here is the arc length of a sector, and right over here is the area of a sector. What we want to look at in this video is this and this, the derivation. But of course it stems from the derivation of a circle's area and a circle's circumference. In many of these figures or the shapes which are in some way related to a unit circle, you know, unit circle is very well described using trigonometry. In any of the shapes which come off the unit circle or even a sector, and in the integral procedures, the trigonometric function somehow, or the trigonometric integration procedure somehow make their way into the integration procedure of these formula derivations. And I've talked about this in the video where the ellipse area, calculating the ellipse area part 2, and also in the circle calculus video, that in many instances this pops up in these integration procedures. And I want to bring this up again in this video only as a shortcut, because when this part comes up, we're gonna expedite it. Regardless of what lies over here and what lies over here with regards to the upper and the lower limit and the coefficient, this you know by the power reducing formula is going to come into shape as 1 plus cosine 2 theta over 2 d theta. And when you split this further, I should have probably just put a single arrow here, but who cares. This will come out as 1 over 2 d theta. There could be a coefficient sitting here and the limits over here, and this right here would be 1 over 2. Again, there's a coefficient sitting over here. This is my plus sign because I've separated everything across a plus sign, and I have cosine 2 theta d theta. When you take this part right over here, this part right here, through its polynomial substitution technique, the fact that you have this 2 theta factor over here and then the antiderivative, it'll always bring something like sine u. And I'm not talking about anything here with regards to coefficients that exist or the coefficients that arise. I'm only talking about this antiderivative sine u, which you will learn in a very upcoming video. Sine u, and you have some sort of interval over here. It can be 0 to pi, or it can be minus pi to pi, or it can be 0 to 2 pi. All of these relevant intervals for which sine is always 0, because sine of 180 is 0, sine of 0 is 0, sine of 360 is 0. In all of these instances, in these relevant derivations, this portion of the formula will always zero out because this part zeroes out. So when we come at this stage, we're only going to look at this part, meaning this part right here, and when this step comes in, we're going to ignore this because this is going to zero out, and we'll only continue on from this point onwards in our derivation procedures. From this point onwards, what are the interval might be over here, and what are the coefficients might be attached to this 1 over 2. So for the first part of this derivation procedure, we're going to be looking here at the sector formula, how the area of a sector is calculated. And you know it starts from the area formula and you multiply by that factor I've already talked about. And I'm gonna expedite through these procedures because I presented many of these same procedures in the circle calculus video that came out not too far long ago. It starts again from this formula for a unit circle, x squared plus y squared equals r squared. You know we're looking at here derivation along an x-axis from minus r to r. We have to convert this into a function. Y is equal to square root of r squared minus x squared. We've converted this into a y equals format. So r squared minus x squared, but that only captures this top part. We have to look at the area of this entire aspect, up and down. Therefore, I've added this 2. It compensates for the loss of the lower part of that graph by means of this radical. So I brought it here 2 times that. And we're also going to employ this shortcut property of a integral for even functions. You can change this from 0 to r and bring this 2 with that. And then we have this 2 sitting over here. We're going to multiply the two 2's and we'll get a 4, and now we have r squared minus x squared dx. Remember, we have to start here with the area calculation or derivation for a circle, then we convert that into a sector. We'll quickly go through this. You have what over here is an expression that has within it a trigonometric properties. You can make the following substitution: a is equal to r, x is equal to r sine theta, dx is equal to r cosine theta, and the intervals which arise, theta 1 is equal to 0, theta 2 is equal to pi over 2. And all of a sudden everything becomes like this: 0 to pi over 2, we have r squared minus r squared sine square x, you've seen this actually, sine square theta, and then r cosine theta. When you simplify all of this part in the radical using trigonometric Pythagorean identity, sine square x plus cosine square x equals 1, you get root of r square cosine square theta, and you have sitting out here r cosine theta d theta. You can simplify all of this. The square root of r square cosine square theta is r cosine theta, which multiplies with exactly what's right over here, and you get r square cosine square theta. This r square can be brought very well along here outside. You end up having 4r square from interval 0 to pi over 2, and then here the magic bullet that I was talking about, cosine square theta. We're only going to take it down from its one path. The other path we're not going to talk about, and that path which we're talking about is 4r square 0 pi over 2. We have 1 over 2 d theta, and these you will learn when you do trigonometric substitution. These shortcuts will come apparent to you. We can bring this 1 over 2 out. We get 4r square over 2 from 0 to pi over 2 d theta. This becomes 2r square, and you integrate d theta with respect to this integral. You just have theta, and then you have pi over 2 and 0, and we're still here on the area formulation, area derivation right here. When you integrate this, you have 2r squared times pi over 2. The denominator 2 and the numerator 2 cancel out. You get pi r square. The area of the formula has been derived. Now to get to this area of sector, all you have to do is nothing more than multiplied by your factor theta over 2 pi. When you do theta over 2 pi, the pi's cancel, and you just have this formula come right about as I've shown you that at the beginning. So in a very simplified process, knowing the derivation of the circle, you can do this extra step and go to the derivation of the sector area formula, area of a sector. And you know a sector looks something like this. determined by an r and determined by a theta which has the opposing end s. But when we're talking about areas, we're talking about this part in between. So the area sector is determined using this procedure as you see before you. Very quickly note for this sector arc length determination, which will stem from the circumference of a circle determination, everything will start again from this equation of a circle, coordinate geometry equation of a circle, or a unit circle if you want to call it. It represents a complete circle. When we're talking about arc length, we still have to solve for y. Y is equal to r squared minus x squared root. When you graph this, you're basically looking at this top portion from minus r to r. But we're not looking at areas anymore, the area between a curve. We're looking at only this part right over here. This, from this point to this point, the length of this arc. And this is represented by this equation. But when we're talking about circumference of circles, we have to account for all of this. So remember, you always have to multiply by that 2 to determine the complete arc length or the circumference. So keep in mind that when we're looking at these arc lengths or circumferences, we're not looking at areas between curves or under curves. We're looking at this external perimeter or the circumference portion of these curves. To derive the formula for the sector's arc length, which you know s is equal to r theta, s is synonymous with arc length, you have to think back to what I presented here in the circle calculus video not too long ago. Was this formula, which employs over an interval an integration of a derivative square. And if you think back to that formula, we won't talk too much about it because I'm referring you to that circle calculus, the circles through a calculus approach video, and I've presented you some background on this. And that has to be employed to determine this, because you have to determine through integration the formula for a circle circumference, and by this factor you get to the arc length. What we have to do is basically find the derivative, and I've shown you that derivative procedure, and I will quickly go through this derivative procedure over here. You know you have to look at this formula right here, x squared plus y squared is equal to r squared, and you have to differentiate it like implicitly. You have 2x plus 2y dy over dx, and I'm referring you to that circle calculus approach video to see all of this. You have to solve for dy dx. dy over dx is equal to minus 2x over 2y, which is equal to minus x over y. But we're trying to determine this right here, which will be representative of this aspect right here. But we know y is equal to all of this, so you rewrite this minus x and you substitute that y and you get r squared minus x squared, and this right here becomes a factor which will come right over here. And you'll integrate it again from minus r to r. So we don't have area over here because we're not talking about areas, we're talking about arc lengths. So it goes from minus r to positive r, minus r to plus r in this formula right here, square root of 1 plus minus x over root of r squared minus x squared, all of this square dx. You have to simplify this. Let's simplify this right out here. Within that radical we have 1 plus x squared over this radical square is just r squared minus x squared. You do a common denominator. Remember, I've shown you all of this in depth in that circle calculus approach video. You can see it over there. Common denominator r squared minus x squared. Here on the top you have r squared minus x squared plus x squared. These cancel out. What you end up having is r squared over r squared minus x squared. When you have this, you can separate this by means of properties of radicals to this. This can come out as an r. This is simplifiable to just an r. All of this simplifies to this. R minus r, you have r divided by this. Square root of r squared minus x squared dx. At the end of all of this procedure, we must not forget the very important condition, and we can probably incorporate it right here. If you're looking at a circumference of a circle, it's a whole circle, but by means of this function over here, we delimited everything to a semicircle, and we must bring in that times 2 to capture the entire circumference. And we can just do that right over here. Bring in that 2 to compensate for this loss of this part by means of this equation and the procedure over here. So we have 2 r, I'm bringing this r outside. Integral minus r, you have dx over r squared minus x squared in a radical. Right here, I am seeing over here a hidden trigonometric expression. I can do again a is equal to r, x is equal to r sine theta, and dx is equal to r cosine theta d theta. I can create new intervals. Theta 1 is equal to, and I'm seeing the opportunity here to bring the even property of integrals. I can make this procedure of creating intervals easy by changing this minus r to, and I can multiply everything by 2. That brings it as a 4. I have 1 2 coming from right over here, the last portion due to the radical, the other 2 coming by means of the even function or y-axis symmetry property of integrals. Minus r to r is the same thing as saying 0 to r, but multiplying everything by 2 in terms of your integral, and this 2 and that 2 makes it a 4. Let's calculate these intervals. Theta 1 by means of this formula you know is going to be 0. Theta 2 by means of the same formula where the x is equal to r. These are my x values, x1 lower limit, x2 upper limit, which feed in over here, and I get pi over 2. So now that I have my upper and lower limit, new limit, interval limits determined, I can bring them in. I have theta 1 as 0, theta 2 as pi over 2. Remember, all of this we will learn very well. I have dx is r cosine theta. We're just resubstituting these substitutions. In the denominator, I have everything here, square root of r square minus x square, which is this square, r square sine square theta. You know all of this will simplify into r cosine theta. Think about it. By means of isolating the r square and by means of bringing that trigonometric identity, Pythagorean identity, you'll get r cosine theta. The one benefit I'm seeing over here with this circumference formula is I'm not having to use that shortcut because things are cancelling out. So I'm not seeing cosine square theta play out, so I don't have to worry about that provision or condition I was talking about, the shortcut condition, because we're not seeing this cosine square theta come into picture here at all, which is good because things cancel out. When things cancel out, what we are left with is 0 pi over 2 d theta. When you integrate this, you're just doing the antiderivative of this d theta with these intervals. What you end up getting is a 4r with this theta coming out, and from pi over 2 to 0. When you do the direct integration of what you're seeing over here of this antiderivative, you get 4r times pi over 2, which you know is right now the entire derivation procedure for this circle's circumference, from which we'll do the factor to get to the arc length. 4r times pi over 2, calculate it out. You're doing half of 4 times pi r, you're getting 2 pi r. When you multiply this by your factor theta over 2 pi, because a sector is a fraction, a proportional fraction of a circle, you get to this arc length formula, and you can see it 2 pi r times theta over 2 pi. The 2 pi's will cancel out, you just have r theta left on the top, and it's done. So keep in mind, in the area formula for the sector, you have to use that shortcut because cosine square theta came into picture, and then you eliminate one side of that integral, which will go towards 0, and you only work with the other side. In this circumference formula for the circle and for the arc length, things cancel out, so the cosine square theta integral does not come into picture, and procedures are greatly simplified. But the purpose of this video was to tie in how a sector's arc length, which is this, and a sector's area formula, half r square theta, how they come into view by means of integral calculus and knowing the derivation of the circle's area and the circle's circumference procedures. Because from there is just a single step to get to your desired outcome. I hope you enjoyed this video. Thank you for watching. Have a nice day.